Hey guys, welcome to the LearnAP Chem livestream. Today we're just going to be going over whatever questions you may have about this week's videos or any other topics in AP Chemistry. So if you're confused about any topic or any specific problem, be sure to ask away in the comments. Otherwise, you know, I'll just sort of just get started here. Alright, so let's go over last week's videos. Okay, so we started by talking. Okay, and I see we have a question already, so that's good. Alright, so Arnold asked, a strip of magnesium metal is placed in a solution of iron 2 chloride. Find the balanced equation and find the oxidizing agent. Alright, so let me write this out for anyone who is watching. Okay, so I'll switch colors here just so it's a little more clear. Alright, so just to start out, if you were confused, iron 2, that means that my iron ion has a charge of +2. I don't know, maybe that was confusing, maybe that wasn't, but just figured I'd spell that one out to start. Okay, so let's write our unbalanced chemical equation to start. So a strip of magnesium is placed in a solution of iron 2 chloride. Notice that I'm leaving space to add coefficients. And I guess we're assuming that a reaction has taken place. So remember the charge of magnesium +2. Magnesium is an alkaline earth metal. And then Cl is -1, so MgCl2 plus Fe. Okay, and so looking at this, I can see right away that it's balanced. And one thing to note here is that this says magnesium metal, and that's very important. That's how I knew to write this as just Mg. Anytime you see the word something metal, that means that it's by itself and it does not have a charge. It's not an ion. So knowing that, this was relatively straightforward to write out. Alright, so we want to find the oxidizing agent. Alright, and so quick note about this. The oxidizing agent is not the one doing the oxidation. So to sort of think about this a little better, you want to think about your travel agent. Who is doing the traveling? Are you doing the traveling, or is your travel agent doing it? It's sort of the same thing. The oxidizing agent isn't doing the oxidation, and your travel agent isn't doing the traveling. Okay, so to write this out, I'm going to write this very explicitly. Alright, and so I see that you had trouble determining the products of the equation. This one is, this is what's called this is single replacement. So anytime you see a metal and some other compound with a metal and a non-metal, you can assume that they're going to switch. Oh, okay, like on the equation I'm writing now. Okay. So I wrote out very explicitly what's happening to each element. So, all right, I'll make a little table here. Product, reactant. All right, so sorry about that. Mg starts. Why would you put a subscript of 2 on the Cl? So shouldn't it just be Cl with a minus charge? No, because we have 2 of them in MgCl. Mg is a +2 ion. Chloride is -1. So we need 2 chlorides to bring us back to a net 0 charge. Does that sort of make sense to you? And then again, but as an ion, it's just Cl minus. Okay, I see what's confusing you. Maybe this is a little more clear. We have 2 Cl minus ions, not Cl2 all -1. I apologize for the confusion. So, alright, hopefully that cleared up any confusion you had. So, going back to our table here, as a product, Mg is just Mg, but as a reactant, it's Mg2+. And then I'll add in this third column. What can we say? Mg lost 2 electrons. As a product, iron is +2. As a reactant, it's just iron. So we can say that iron gained 2 electrons. Cl just says Cl minus. So we can say, sorry, nothing happened. Alright, so remembering that our oxidizing agent isn't the one doing the oxidation. So oxidation is defined as the loss of electrons. Or I'm sorry, isn't doing the oxidation, isn't, that was sort of unclear, isn't being oxidized. Alright, so we can see that, in fact, Mg is being oxidized and iron is being reduced. So we have to look for something that's changing electrons but is not being oxidized. So we can eliminate Cl because Cl is not doing anything. We can eliminate magnesium because it's the one being oxidized. It's not the oxidizing agent. So therefore, Fe, or I'll just write iron, is the oxidizing agent. Alright, so Arnold, hopefully that answered your question. If it didn't, let me know, or if you have anything else, anybody to that matter, ask away, but otherwise we can sort of move on to other stuff. Yeah, essentially the same thing. Technically, I apologize for writing it that way, but on the AP Chem test, you would want to write the actual, and I wrote these backwards. I dearly apologize for that. You want to write the reactant that this belongs to, which is FeCl2. That's not how we do it in my current chemistry class, so I apologize for not doing the AP chemistry sort of norm, but the idea is that Fe is the oxidizing agent, but in the reactants it's FeCl2, so that's why it's the answer. And then again, if anybody has questions, be sure to stop me along the way. Alright, so we can start going over last week's videos. We first started talking about percent composition. And then I said that percent composition of A and B is the molar mass of A over the molar mass of B, where A is some element, maybe it's usually an element, but it can also be a polyatomic ion, so you might be asked for the percent composition of NaNO3, or of NO3 minus in NaNO3, and so here NO3 minus is going to be our A, but normally it's just going to be an element. Okay, and so to find, and this is just simply, we have to find molar mass of A, molar mass of B, and we've already gone over that in previous videos. Again, it's just factor labeling. Pretty much you're just plugging it into existing knowledge. Alright, and so I also talked about empirical formulas. So it's sort of like, if you think about in math, 2 plus 4 could be simplified like this. And that's sort of the idea of, or probably a better example is 10 over 10 over 6 could be rewritten as 5 over 3. And that's the idea of empirical formulas, is that we're essentially just reducing our subscripts. So here H2O2 written empirically is HO. You only want to worry about empirical formulas when you're doing problems that explicitly deal with it. So I guess an example would be, let's say you were given a reaction like this. You would not want to then say, oh, let me write that empirically, because that would be wrong. You should only worry about empirical formulas when we are trying to find them. Alright, and so I just want to get your feedback on this. This is sort of a tough concept, so we can go over this again. So the first thing is that they'll give you the grams of each occurring in the compound. And your job is to find the empirical formula of that compound. So it's like we have 34.3 grams of barium, 17.7 grams of chlorine. What is our empirical formula? And in this example, it was, if you just knew BaCl2, it's pretty obvious. But sometimes they'll give you a bunch of nonmetals or metals, more metals and nonmetals, and it's not obvious like this. So what you first have to do is find the number of moles of each. So we want to find the number of moles of barium and moles of chlorine. Then we're going to divide all the values you've gotten by the smallest amount of moles obtained. So I got 0.250 and 0.500. So I'm dividing everything by my smallest value, 0.250. And so this just comes out to 1 and 2. And then if we get a fraction, like say this was 1.33 or 4/3, we'd want to multiply through by my denominator, which is 3, to get whole numbers. Because again, you would never see like HO 1/2. That's just not a thing. Okay. So yeah. So that's sort of an optional step here that didn't happen, so we didn't have to do that. And then finally, we want to write out the compound according to the number of moles you've gotten. So our sort of normal naming convention is to write our metal first, so I'll write that out, followed by the numbers I got, which is just 1, so just Ba, Cl, and then I got 2 here, so Cl2. Molecular formulas are basically empirical formulas with an extra step. So what we first want to do is literally repeat that process and find our empirical formula. And then the next thing we want to do is we want to find the molar mass of our empirical formula that we just got. Then we divide the molar mass of the compound that's given. So it will say, so if I like go up here, it'll give me this stuff again, but then it'll also say the molar mass of the compound was X grams. Okay, so yeah, you're absolutely right. Because hybridization, if you think about it, is in large part determined by the number of sigma bonds and our lone pairs. Okay, so anyway, so molar mass of the empirical, or I'm sorry, of our molecular that's given to us, divided by the molar mass of our empirical formula. And that should give you a whole number, and you can sort of multiply through to find the molecular formula. So for example, if I got this was equal to 6, then I'm just multiplying through. 6 times 1 is 6, 6 times 2 is 12, and okay. Alright, and then the challenge problem was just a molecular Formula 1. I can go over that if you guys want, but otherwise I'm just going to move on to gas laws. But again, feel free to stop me at any point. And so that brings me to my next thing that I wanted to say, is that Arnold commented that if you use 22.4 liters per mole at STP, you got sort of a different answer for this. I'm not sure what the right answer was, but or what the answer you would have gotten was if you used this, but it was off by 1 or 2. And what I have to say about that is you would not be marked wrong as long as you explicitly stated that you were using that. So if you said, if you were like doing your work and then you said at, you don't have to write in all caps, at STP 1 mole of gas occupies 22.4 liters, and then did more work and then got an answer that was slightly different, you wouldn't be marked wrong. Even though, and the reason for that is that this goes to more decimal places. In fact, let's figure out what the exact decimal is for that. So at STP, this is just n.08206. We'll use sort of the more accurate R. And then T is, this is in Kelvin, so 273.15, I believe. And so, yeah. And so, I'll do the math here. 0.08206 times 273.15. And we get this. So you can see that it's slightly inaccurate. And so what was happening here is that we're sort of multiplying this by a bigger number, so the error is getting exemplified. But as long as you wrote this out, you'd be fine. Alright. So, we'll talk about what we did in the last video. And we went through, started with Boyle's, and Charles, and Gay-Lussac's, Avogadro's principle, were the 4 that we went over. And You don't have to memorize the corresponding names to each, I highly doubt that you'd be asked on the AP test, whoops, P1 V1 equals P2 V2 is law. It's just more important that you know all of these. So yeah, just memorize P1 V1 equals P2 V2, V1 over T1 equals V2 over T2. This could also be written like so, if you prefer, but I find that this just gets confusing. Similarly, this could be written like so. But okay. So yeah, just memorize those four. You can ask literally anything about AP Chemistry. I'd also add that we had a calc live stream an hour ago, and those are every Sunday from 4 to 5 p.m. Eastern, if you want to ask calc questions. But literally any question on AP Chemistry is fine. Right now we're just sort of running through what we did on our last video. And Arnold asks, how important is it to know the scientists who discovered the neutron, the charge of electrons, proton? Is knowing how they discovered it more important? You do need to know the names of the scientists who discovered these things. Let me scroll up to okay. So in the absolute first video we ever did on the channel, we talked about all this stuff in a sort of history of the atom section. You're probably well aware of that. But you do need to know the names of the scientists, and you need to know the names and sort of what they did. But if you're asking, let's say you had to choose between knowing how it was discovered or the names of the scientists, I would go for how it was discovered, because that is more important. Is there any better way to memorize solubility rules and their exceptions? So my guess is you're asking for do I have a mnemonic device? And Arnold's got it right there. NAGSAG. Actually, I haven't heard of that one. I'm guessing that's nitrates always nitrates always. Arnold, if you could elaborate on NAGSAG, that'd be great. I don't myself know any mnemonic devices. I just straight up memorize them, but I'm sure you could just sort of a quick Google search should yield some good results. Okay, so I've seen it. Okay, nitrates, acetates. Okay. And then group 1. And remember remember groups versus periods. So if we go back here, this is a period, this is a group. So our group 1s are going to be these right here. Going back, these are always soluble. Sulfates ammonium group 17, and this is like F minus. These are also always soluble. So yeah, neg seg. Thank you for that, Arnold. That's a good mnemonic device. Okay. Yeah, if anyone else has any, that would be awesome. And so, yeah, so remembering group 17 is everything with 7 valence electrons, and group 1 is everything with 1 valence electron. All right. I don't believe we got to kinetic molecule. Okay. One thing I would say about solubility rules is that a lot of times you can sort of infer whether something is supposed to be soluble or not. Like, let's say we have Na, let's see, H, I'm trying to think what a good example would be. So let's say we had something that yielded HOH and NaNO3, and I wasn't sure whether this was soluble or not. I could pretty quickly just see that, well, this is a liquid, so I can almost guarantee that NaNO3 is going to be aqueous. So that's one thing I'll say, is that if you have a product that is clearly insoluble, you can almost guarantee that the other one is soluble. Or on the reverse hand, if you knew that this was aqueous, whatever you had over here you knew would have to be a precipitate. So yeah, that's just sort of a good thing to know. So if you guys have any more questions about solubility or anything, be sure to ask, but otherwise we'll continue talking about the last video, which is gas laws. And this should be this should be very easy to come to you. PV equals nRT, pivnert. And then note that given an ATM, this can be given in like other units like torr or millimeters of mercury, but note that that's going to change your R. V is always in liters and N is always moles. And then your temperature is given in Kelvin. I explained that it wouldn't make sense to use Celsius because you could have -5 degrees Celsius and then you're going to get a negative pressure or negative volume, which doesn't really make any sense. Alright, so then we went through an example problem, and then this one so this one is a little bit different, and we can derive it from PV equals nRT, but I don't think you would ever be asked to do that, and you can just sort of memorize PM equals DRT. And this is sort of a really important shortcut to know. that PM equals DRT. So, yeah, no PM equals DRT, I guess. STP, and then this is just some more shortcuts. At STP, the volume of 1 mole, and then of an ideal gas, is 22.4 liters. Temperature is 0 degrees C, not 0 Kelvin, so you wouldn't be plugging in 0 for P. And our pressure is 1 atm. Alright, partial pressures. This one's a little more tricky, but I find that with practice it actually becomes very easy to do, in that the sum of our pressures equals the pressure of 1, pressure 2, pressure ... 7A are the fluorines. If we look back at the periodic table, we can see that it's in fact 17. But yeah, 7A is also halogens. Okay, so let's see. This is not what I was talking about. Apologize. So what you have to do to figure out what these partial pressures actually are is use what's called the mole fraction. And I'm not sure why you can't put a link in the chat. Maybe you want to just, if you send an email to me, Arnold at info@LearnAP, I should be able to put it in the description for you guys. So if you want to do that, you can go that route. Otherwise, you know, whatever. Okay, so finding these partial pressures deals with the mole fraction. And what that means is mole of gas X over the mole of the total. Alright, and so that's basically what we went over in our last videos. So, I've been sort of rambling. I want to open up the floor to you guys. You don't have to have like a specific question. Maybe you just want to ask about like a certain topic that you want me to explain, or something of that sort. But otherwise, I can sort of... Alright, and I see that Arnold sent me... Alright, so I'm just gonna quick add the solubility rules into the description. I apologize. Okay, so this is that's where you want to go to find solubility rules. Alright, so thanks for that, Arnold. Hopefully that'll be helpful to some people. But yeah, if you guys have questions, just submit them, or like any topic that you'd like me to talk about. Otherwise, we can sort of just do some miscellaneous gas problems, because that's sort of what we were going over in last week's video. Okay. So let me just get my practice problems here. 1 second. All right. A sample of CO has a pressure of 58 millimeters of mercury. Okay, I'll just continue doing practice problems, but if you want me to explain Vesper, I can do that. Maybe after or at any point. There's a pressure of 58 millimeters of mercury and a volume of 56.0 milliliters. If CO is transferred to a container with 1 liter, what is the new pressure? Okay. Alright, so let's think about how we want to approach this problem. We want to remember that I guess sort of the instinct in these type of problems is you see gases, you see pressures, and you immediately think PV equals nRT. But here, that's actually not the way we want to go. You could use PV equals nRT, but it's going to take way longer. What you want to use is P1V1 equals P2 V2. Alright, so the way to do this is simply plugging in our knowns. So P1, 58 millimeters of mercury, 58. V1, 56.0 milliliters. But I see that, or I'll just write this out as 1.00. Okay, so I can see that this is in liters and this is in milliliters. And to do this problem, all my units have to be the same. So I'll actually convert my milliliters into just plain liters. So 0.056. Remember that 1,000 milliliters in a liter. Okay, equals P2, which is our variable we're trying to solve for. But you didn't state it's at STP, that's why I began with PV equals nRT. It actually doesn't matter what our temperature is or what the number of moles are in this problem, because we know that these are proportional regardless of the temperature and pressure. I guess I didn't explicitly say they are at the same temperature. Actually, no, that doesn't matter at all. Yeah, so regardless of their temperatures or number of moles, these are going to be proportional as long as those two quantities are held constant, which in these problems you should assume. Okay, so P we're trying to solve for, V is just 1. Alright, and so let me get out my calculator to solve this. So 58 times 0.056 equals 3.248. Alright, now we want to think about what my units are. And so, as I alluded to earlier, that the units of the P's have to be the same as the V's must also be in the same units. Well, since P1 is in terms of millimeters of mercury, that's what P2 is going to be. Torr is also fine, but that's just because 1 torr equals 1 millimeter of mercury, but the only reason that torr is also fine is because a torr is the same thing as a millimeter of mercury. Okay. If you guys don't have any more questions, I can do some more practice problems, but I first want to just very quickly talk about Vesper because Arnold asked about it. I think the explanation is very simple. Let's say that we have CH4 and they'll be pretty easy to work with. They're not gonna give you like, they wouldn't give you something like that. In general, yes. You know, they're not trying to test your division and multiplication skills. They're trying to see how well you know AP chemistry. So, like, I wouldn't be really worried about honing in your division or subtraction skills and such. So to answer your question, yes, you can reasonably expect that the arithmetic will be easy. Okay, so I'm gonna quick draw these out as just the electrons being shared. Normally these are bonds, but for the sake of this example, I'm drawing electrons. And so all Vesper theory is saying is that these electrons here are repelling each other. And since we can predictably say that these are repelling each other, we can basically say that they're going to take this shape. And that's all Vesper theory says. It's like a very complicated explanation and abbreviation that's actually something pretty easy to understand, in that the electrons are repelling each other, and because of that we can predict what shape and bond angles are going to be. Okay, so seeing that we're in sort of the last 10 minutes again, if you have questions, you can ask away. Otherwise, I can move on to another practice problem. Okay, so I'll give you a more theoretical question. Considering I'm sorry, I always misspell Avogadro. No, I'll do Boyle's law. If the volume of a gas decreases and all other factors except for pressure stay constant. What happens to pressure? Does it increase? Does it decrease? Alright, so this is a little more of a conceptual question, but we can actually find the answer pretty easily just knowing our formulas. So Boyle's law here is P1 V1 equals P2 V2. And so we're saying that we have some pressure. We'll just call that 1. And some volume, we'll call that 1. If our volume decreases, so we'll say V2 is 0.5, what happens to our pressure? And I can solve this and see that I went from a pressure of 1 to 2, so our pressure is increasing. And Arnold got it exactly right. Pressure increases if volume goes down. And that should make sense. If we have this gas in here and then I shrink my volume way down, I'm going to have more collisions more frequently. So my pressure is going to increase. So yeah. If you guys don't have any more questions, we can sort of continue writing the practice problems. Let's see. Can you walk me through this problem? That means the gas. No, the gas isn't necessarily moving at a faster rate. That would describe, well, it's not moving at a faster rate, but since our volume is decreasing, it's hitting things more frequently at that same rate. And so no, temperature we're assuming is constant. So we're assuming that the rate of motion of our gas is staying constant. And the only reason that pressure is going up is that we have a smaller box, so we have more collisions. Yeah, glad I could help. And I see we have a question, so I'll see if we can't do that. Okay. What volume of 0.150 m NaOH is needed to react completely with 3.45 grams of iodine according to the equation? Okay. Let me write this out. Uh, 3.45 grams of I2. And then we're given the equation. Oh, whoops. Okay. So the first thing to do is to just say that we have 0.15 moles of NaOH per 1 let me get a different color. Alright, maybe this is a little obvious, but I find that it's always helpful to write it out. So the first thing we want to do is find out how many moles of iodine we have. So 3.45 grams I2, and then I don't know the molar mass of iodine off the top of my head. Molar mass of iodine. Alright, 126.9 times 2. And then so we have 253.8 grams of I2 per 1 mole. Okay, so 3.45 divided by that is 0.0136 moles. Alright, so to react with this, we need to have I'm trying to think about the best way to explain this. Okay, so let's say for 6, actually here's the best way. Alright, so let me get myself a little more space here on the problem. Okay, whoa, that is not what I wanted to do. Okay, there we go. So 0.0136 moles of I2. Now I want to convert that to moles of NaOH. So for every 3 moles of I2, we have 6 moles of NaOH. Alright, and so this is going to give me the number of moles of NaOH, but I'm actually after how many liters of solution, so I can use this right here to convert back to liters of solution. So I have 0.15 moles of NaOH per 1 liter of solution. So I'll solve this, just plugging it in. This you could reduce to just 2, so 0.136 times 2, all divided by 0.15, and if I did not make any arithmetic mistakes or anything else otherwise, the answer should be 0.181 liters of solution. Is that the right answer? If that's not, I can check my arithmetic, but essentially what we're doing here is we're taking our grams of iodine, converting it to moles, and to react completely, we need 6 moles of NaOH per every 3 moles of I2, and then I'm after liters of solution, so I just convert that using the molarity. Alright, and so I see that's the right answer, and glad that I could help out. Hopefully that made sense to you. Alright, so we have reached 6 o'clock Eastern, so I want to thank everybody for tuning in to this week's AP Chem live stream. Next week, we're back on our same schedule, 4 to 5 for Calc, 5 to 6 for Chem. So yeah, hope you guys found that useful, and I will see you next week.